Hey guys, in this lesson we're going to learn about the factor label method and we'll do some mass-mole conversions. The bookwork associated with this lesson is here. It's going to be 27 to 36 on pages 50 to 51. And I want you guys to start your classwork page of notes with that, and then continue here with the aim. What is the relationship between mass and moles? And then follow it with these particular do now questions. We will work on those in class tomorrow. And to do these mass mole conversions, we're going to use some skills under the set of skills that we call stoichiometry. And we're going to need a conversion factor to start. A conversion factor is just it's just a ratio that relates one thing that you do know to something that you don't know. All right, so for example, if I asked you a question, how many donuts are in 3½ dozen, some of you could probably do that in your head. But there is a conversion factor you would have to apply, even if you did do it in your head. And that conversion factor is that every dozen contains 12 things. So the conversion factor is a ratio, right? And does that mean that this is the correct ratio? Is 1 dozen, are there 12 things in a dozen, or are there a dozen in 12 things? In fact, both of those things are correct. Neither one of them is untrue. And the way I can prove it is that if you think about the real numeric value of each of these things, the 1 dozen and 12, their numeric value is the same thing. Even if the sort of multiplier here is a different multiplier, they're representing the same number of items. And when you take the same number of items and you divide it by the same number of items, you always get the same answer, and that is 1. So, if either way you write this is equal to 1, then it doesn't matter which way you write it. What we will do later in this lesson, though, is we will choose to write, let's say, 1 dozen over 12 things, or 12 things over 1 dozen in different scenarios, because they'll help us in different ways. So, allow them both. All right, let's start off with this question. How many donuts are in 3½ dozen? And we will apply the conversion factor of dozens and things. So we'll just start by writing down the given information, which is 3.5 dozen. And when I consider what part comes next, I should think, do I really want to be doing 1 dozen over 12 things, or 12 things over 1 dozen? And I would suggest that we do the following. I suggest doing it in this particular way. And the reason why is because if you do it just like that and not in the opposite way where it's 1 dozen over 12 things, then you have the wonderful ability of canceling the term dozen with the term dozen. The reason for that is because you can think of this as really just being over 1 and that you're multiplying these two fractions. And when you multiply two fractions like that, this term can cancel that term. Okay, but what does that leave behind? It leaves only one unit, which is the unit things. That's the unit that we wanted. So all we need to do is combine these two fractions the way we would combine any two fractions, which is to say we'll multiply through on the top and get 42. And I just did that by multiplying the 3½ times the 12, the same as you would with any two fractions that are being multiplied. And the unit for that is the only unit that's left behind, or things, which in this case is donuts. Basically all I did was I started with my given information. I thought of a conversion factor, which in this case would be 12 things over 1 dozen, and I designed that artfully so that dozen would be on the bottom, so to cancel this dozen that was on the top. And then the only unit that was left was things, which is the one I wanted to start with, and I multiplied through on the top, and I multiplied through on the bottom, and I got 42 over 1, or just 42 things, or donuts. So that's the basic idea behind the factor label method, and let's put it to work. So before we get into these sort of heavy, like mass mole conversions, I have a short video about the mole that I'd like for you to watch.
In this video, you will learn what a mole is, and why chemists work in moles. A mole is quite simply a specific number. In life, we might ask for 12 or 1 dozen eggs, or a pair of socks for 2, or a ream of 500 sheets of paper. A mole is exactly the same. It's just a number, and is specifically 6.02 times 10 to the 23. We could have a mole of eggs, a mole of socks, or even 1 mole of sheets of paper. However, in chemistry, we normally use it to represent atoms or molecules. This is because atoms are so small. It's just a convenient term to represent massive numbers. And a mole is a massive number. It's 602 with another 21 zeros after it. Just to give you an idea of how huge this number is, if you took 1 mole of marbles, they would not only cover the entire Earth's surface, but they would cover it to a depth of near 3.5 kilometres deep. As you can see, a mole is a mind-blowingly large number. And the reason for this is that atoms are just so incredibly small. Now you can see why we use the term mole. It is just a convenient way to quantify huge numbers. It's much easier to talk about 2 moles of sodium rather than 1.204 times 10 to the 24 atoms of sodium. And it's much easier to mention half a mole of water rather than 3.01 times 10 to the 23 water molecules. So what exactly does 1 mole of atoms or molecules weigh? Well, this just depends on how big your atoms are. Just because we've the same number of atoms in 1 mole, it does not mean that they are all the same size. For example, you're probably aware that hydrogen atom is much smaller than a heavy gold atom. So 1 mole of gold will weigh much more than 1 mole of hydrogen. Just in the same way that a dozen eggs would weigh more than 1 dozen grains of rice.
So one note that I want you to write down for sure before I do any of this math is that like the coefficient that you might see in front of a formula, like if you were to see this formula and maybe there was a coefficient like an 8 here, for instance, then that would represent the number of moles of that substance. So that's just a fun fact that the number of moles of the substance is the coefficient in front of a formula. All right, so let's do our first question. How many moles of oxygen atoms are in 1 mole of Mg3PO42? So since there are 8 atoms of oxygen in each unit of Mg3PO42, and there is 1 mole for 1 unit, then that means there are 8 moles of oxygen atoms in a mole of magnesium phosphate. And on to a hard question. What is the mole equivalent of 39 grams of lithium fluoride? So if we start with 39 grams of lithium fluoride, and we know that we need to multiply it by a conversion factor, we can be really smart about what that conversion factor actually is. In our previous example, it was dozens and donuts, I believe, or maybe it was things, but there were a dozen on the top and thing on the bottom, or thing on the top and donuts on the bottom, and the one that I ended up choosing was the one that canceled the original unit. So what I want to have down here is definitely gram, because I know that ultimately the gram that I just wrote here will be canceled by this gram. But the unit that goes on the top in the numerator is going to be the unit, presumably, that you want to keep. And in this question, I want to keep the mole. So let me introduce MOL, which is the official way of writing the unit mole. And now for the hardest part, we need to figure out what numbers go here, because it isn't just a unit. If you look at this, you see grams and moles, and this has the same units in it as the thing that we learned about yesterday, the gram formula mass, whose unit was grams per mole. But can moles per gram be the same thing as grams per mole? Absolutely. You might remember from the previous slide that if we had a 12 up here and a 1 down here, or if we had a 1 up here and a 12 down here, that both of them were actually equaling the same quantity, which is 1. So whether I write moles per gram or grams per mole makes no difference at all. But in this particular case, it's much smarter to write moles per gram, because if I do, it'll cancel the grams that are up here. So all I need to do to finish this up is find the number of grams that are in a mole of lithium fluoride. So since lithium has a mass of 7 grams per mole, and because fluorine has a mass of 19 grams per mole, then I know that the mass of a mole of lithium fluoride is 26 grams per mole. And previously I had decided that I should really write this as moles per gram, so here I go. Notice that I kept the 26 near the term gram, and I kept mole with the number 1, which is really what this says, 26 grams in 1 mole. So all I have to do now is to remember that the 39 grams can be thought of as 39 over 1, and that I would combine these two the same way I would combine any two fractions, which is to say multiplying through. So 39 times 1, after the grams cancel, would be 39 moles, but it would be over 26. So after we do that final division, we get 1.5 moles. Final answer. Not so bad, huh? Let's try another set of practice questions. So in these, we're going to be doing mole mass conversions. So if I'm given the number of moles, but asked for how much mass that would be, we can still use our factor label method. Everything's going to be perfect. So for this first question, where we're asked to give the total mass of 0.75 moles of sulfur dioxide, let's start off the same way. Let's start out by writing what we know. And now we need to multiply by a conversion factor. That conversion factor can be grams per mole. We just need to figure out what the grams per mole, or the formula mass of sulfur dioxide, is. So since the mass of sulfur is 32 grams per mole, and because the mass of oxygen is 16 grams per mole and there are 2 moles of it, then we can also say that the entire molar mass is 64 grams per mole for sulfur dioxide. So do I want to write 64 grams over moles, or do I want to write 1 mole over 64 grams? So in this case, I suggest that we write 64 grams over 1 mole. And the reason for that is because the mole on the bottom will cancel the mole on the top. And then we just need to multiply through on the numerators and the denominators. So at this point, I'm just going to multiply 0.75 times 64, and I'll get 48. The only unit that remains is grams, and that's great because that's my answer. Alright, another example. What's the mass in grams of 2 moles of sulfuric acid? I have an extra challenge here, which is, what is the formula for sulfuric acid? Well, it's H2SO4, but in case you're worried that you won't remember that every single time you're asked, I have a suggestion. Check Table K. The Regents call it the table of common acids, and if they're going to ever ask you a question about a random acid like they did just now, then it's going to be on Table K. So H2SO4, it's on Table K. Let's go ahead right now and find its molar mass. So hydrogen has a gram formula mass of 1 gram per mole, but there are 2 hydrogen atoms here. And sulfur, as we discussed, is 32 grams per mole. And oxygen is 16 grams per mole, but there are 4 of them in this case. So I'm going to add all this up to get 98 grams per mole. The question is, will I need to write 98 grams per mole, or will I need to write 1 mole over 98 grams? So let's start by writing down what we've been given, which is 2 moles of H2SO4. And we're going to multiply it by a conversion factor, which will cancel the 2 moles. So I need to put moles on the bottom, which also means that the 1 goes down here with mole. And on the top, we're just going to write 98 grams. When I multiply through, I get 196 grams, which is the only unit that remains after the moles cancel. Alright, one more. What is the mass of 1 mole of sodium nitrate? So sodium has a mass of 23 grams per mole, and nitrogen has a mass of 14 grams per mole, and oxygen is 16 grams per mole, but there are 3 of them. So when I add them all up, I get 85 grams per mole. And in the question, they just asked me for what's the mass of a mole of sodium nitrate, so I've already arrived at my answer, but just to put this into our sort of formula, just to make sure we have the right answer, then start with your given, so you write 1 mole. You multiply it by a conversion factor, which in this case is going to be 85 grams over 1 mole. The moles will cancel, and then you get 1 times 85, or 85 grams. Alright, So we are now at our pair up. And this pair up, I just want you to copy down the questions without solving them. Same thing for the summary questions. We'll do these in class next time I see you. Hope you enjoyed the video, hope you took great notes, and thanks for watching.